It's the 11th. So it's how much energy it would take to vaporize 1 mole of a liquid, and the stronger the internal bonds of the material, the more energy it takes. Water is interesting. So every material has an inherent molar heat of vaporization. This basically means, higher and lower boiling point. Though, remember, molar heat of vaporization is an amount of energy, it's not a temperature. Things with higher boiling points tend to have higher heats of vaporization, molar heat of vaporization, because it means they've got stronger internal bonds. Water is weird. It's actually got a higher molar heat of vaporization than we would expect based on all its other characteristics, and that's because of 2 factors. It's got those hydrogen bonds that exist between water molecules, so that's one more bonding force within the substance. It also is a polar molecule. And polar molecules tend to have higher molar heats of vaporization, higher melting and boiling points, because that's one more, they've got those dipoles between them. And it's one more thing that holds the molecules together. So you tend to see higher than you would expect otherwise heats of vaporization. Things that take a lot of energy to get them to go from a liquid to a vapor do make fantastic cooling agents. If you noticed on that chart with your vapor pressures, ethylene glycol has an even higher boiling point than water. Guess where you have probably interacted with ethylene glycol? It's in your car. Does that help? It's got an even higher boiling point than water. Antifreeze. Antifreeze is primarily made of ethylene glycol. So it's got a very high molar heat of vaporization. It takes a lot of energy to vaporize it, which means it can absorb a lot of energy from something else like components of your engine before it would vaporize. Okay, we talked about the transition from a liquid to a vapor, vaporization. Now we got to talk about the transition between solids and liquids. So, freezing, solidification. You can say either, but solidification sure sounds a whole lot smarter. The other phase change between solids and liquids is melting. You knew that. And the freezing point is where you can have equilibrium between the solid and liquid states at a single ATM. That equilibrium equation exists for solid to liquid phase transition, just like it did for liquid and vapor. A solid plus heat energy will give you a liquid. A liquid, if you solidify it, you'll get a solid plus heat out. And that's that whole saving the strawberries on a frosty May night by irrigating the living crap out of them. A trick that I pulled in my garden when we had those frosty nights. The other thing that you can do to take advantage of this specific component and really of the high molar heat of vaporization is this. These are what are called trombe walls. Trombe, T-R-O-M-B-E. And they're a prominent feature of a lot of passive solar homes. So what you have here are giant tanks of water that are in the path of sunlight. What does that do? It acts as what's called a heat sink. It's a reservoir for heat energy. You got that, didn't you? Good. So the water is heated by incoming solar energy. And remember, water takes a tremendous amount of energy before it's going to do a phase change because of the fact that it's got those internal bonds, those internal forces of attraction. What that means is that it's very slow to change its temperature. It takes a lot of energy, which also means that it stores that energy, and as it drops its temperature again, it gives that energy back off to the environment. So the way these work, and you can, I've seen really simple sort of DIY ones done. There was a passive solar home I saw years ago, and they had taken in front of their south bay of windows 5-gallon plastic, like drinking water containers, filled them, capped them, sealed them permanently so they couldn't leak, and then they were stacked against those south windows. So it created this wall of water. Well then, water absorbs the heat, and then after the sun goes down and the water starts to cool, it radiates that heat back out into the house. And you're taking advantage of water's unusually high molar heat of vaporization, and it's called specific heat capacity. Just another, it's an application. These, so those are pretty clear, they're tubes. These are actually some kind of cells with water in them, and I don't know what the material is. And these are both sort of like more expensive, more commercially prepared trombes. But I have done on cold nights in my garden, I've taken 1 liter plastic bottles, filled them with water, and set those around my tomatoes. And those radiate heat back out to the tomatoes at night. There's a product called Wally Water, and it's plastic. It looks like blow-up swim fins, except they're really a series of interconnected tubes, kind of like this, and it's sort of a sleeve of them. Well, there's a little inspout. You fill it up with water, and you set it around your baby tomato plants, and you can put your stuff out a few weeks before the frost date. Well, they absorb solar energy during the day, and then they form this little warm protective teepee at night so that your tomatoes don't get frosted. So again, you're taking advantage of those characteristics, that heat and energy absorption characteristic of water. Okay, so resistance to phase change, oh yes. Molar heat of fusion, on the other hand, is how much energy it takes to melt a mole of a solid. And, same as with molar heat of vaporization. It says heat, but it's not. It's energy. And stronger forces of attraction internally mean it takes more energy to get those particles to move apart. So here we're talking about how much energy it takes to actually break the bonds between the particles. Do you think that ionic or covalent compounds would have higher molar heats of fusion? You might have some experience with this. Ever try to melt sugar? Like in here? Ever try to melt salt? Which one melted? Yeah. Sugar melts no problem. Salt, not so much. It's a problem. So, okay. This is the other phase change that we don't necessarily get to talk about as much. Sublimation or deposition. These are the more unusual phase changes. So we've talked about vaporization and solidification. Sublimation is when you go straight from a solid to a gas. Who here has had a chance to play with dry ice? Where'd you get to play with dry ice? Nice! I need to find a supplier for some dry ice. It's cool. What is dry ice? It's solid carbon dioxide. It's carbon dioxide that has been taken out of the atmosphere and solidified under particular conditions of temperature and pressure. It goes straight from being a solid to being a gas, so it lets off this like cool smoky looking vapor. It used to be used in like special effects to create fog. When I lived in Arizona, I worked in a bakery. I told you this. Got up every morning and did the baking, for about 1.5 years. Well, we baked all our own bread. We baked our own scones and cookies and muffins and pastries. We did not, however, bake all the fancy cheesecakes that were in the big case. And you've probably been in a restaurant where there's a case of like fancy cakes with little, pieces of tissue paper, wax paper between the pieces, whatever. We didn't bake those. They came from a bakery in Phoenix. And they came in frozen. So you want to ship frozen cakes from Phoenix 123 miles across the Sonoran Desert, where it gets up to about 115 degrees in the summer, and in the winter it's still in the 80s, and you want to drive them to Tucson 117 miles, and then you want to drive them another 30 miles. Basically, you want to take a 3-hour ride with frozen cakes in the desert. To keep them well frozen so you don't have any partial unthaw, rethaw, or thaw and refreeze crystallization issues, they would ship them on dry ice. So the cakes would arrive at the restaurant where I worked packed into boxes of dry ice. We had a big restaurant sink full of sudsy water from washing all the dishes repeatedly. So you can take chunks of dry ice and throw them in the dishwater, and it starts to bubble rapidly, and the bubbles come up to little wispy vapor, you know, and then they would pop and leave little clouds of smoke above the dish sink. It was so cool. So if you ever get a chance to play with some dry ice, you know, don't neglect a dish full of, a sink full of sudsy water. Just throw some dish soap, some, you know, room temperature water in there and toss your dry ice chunks in. Hours of entertainment at least. That's sublimation. The opposite of sublimation is what's called deposition. And we see this on a lot of autumn nights, and mostly in the autumn we start to see this. Deposition is when you have something that goes straight from a vapor phase to a solid phase. And do you know what I mean when I say a hoarfrost? H-O-A-R. H-O-A-R, a hoarfrost. When something is hoary, do you know what that means? Frosted, fuzzy. There's a species called the hoary bat, and all of its fur is sort of tipped in white. It looks like it's been frosted. A hoarfrost is when you get like those big, thick, icy crystals on everything. That's a hoarfrost. That is deposition. Where did that frost come from? It came from water vapor in the air. So on a normal night, on a warmer night, we might have a heavy dew, and the grass is wet in the morning because water vapor in the air has condensed into a liquid form. It has condensed on the surface. It's gone from a vapor to a liquid. On a really cold night, instead of condensing, it will actually sometimes, under the right conditions of pressure and temperature, undergo what's called deposition, and it goes straight from being a vapor in the air to being that beautiful crystally hoarfrost. So now you know to look for it. Both of these tend to happen at low temperature and low pressure. You can have sublimation happen in your freezer with water. Has anybody ever had ice cubes that magically vanished? If you leave them in the fridge long enough, very often the ice cubes disappear. That's sublimation. Phase change diagrams, sometimes called a triple phase diagram. Did any of you see this on the ACT? Were there any of these on the ACT?
I think I had one maybe the last time.
They very often show up, though I think when they took it at school here, people said there wasn't one. I have heard of people seeing both this and seeing the vapor pressure diagram. That's why this chapter, I think, actually does more for people in terms of ACT. Maybe I should lead with the phase chapter. Lead with phases of matter. I'm just a graph, there's a song that I don't know the words to. I'm just a girl. No. Okay, so here's the cool part. You can look at this diagram for any substance and know under what conditions what phase change will occur, know under what conditions it will exist in what phase. So this is our old friend water. Pretty simple. If we're looking at things down in this range, what two phase changes could we see along that blue line? Sublimation or deposition. So that's that low temperature, low pressure area where we would see sublimation or deposition. Here, what two phase changes would we see on that line? This one's easy. Huh? Melting, yeah. Melting or solidification, yeah. We would see melting or solidification, either which direction we're going. And what phase changes are we talking about here? Vaporization, evaporation, or converse is condensation. Yeah, so very easy. The triple point is right here, and triple point is this one little tiny blip of pressure and temperature conditions where you can have a mixture of all three phases in equilibrium. Whoa. If you put ice water in a sealed vessel, do you have some water vapor above it? Sure. Do you have some in the solid, some in the liquid? Sure. At triple point, you can have all three of those in equilibrium. You know, generally, if we set out ice water here in a sealed system, at room temperature, what change is going to be happening? Which way is the equilibrium going to be pushing? Towards liquid, or, you know, probably mostly towards liquid, because water is a liquid at room temperature. So the equilibrium is going to be pushing towards liquid. At triple point, it's literally a three-way street, all three phases in equilibrium. Critical point is also kind of interesting. So the question was, you know, if you put all three phases of a liquid, or all three phases of a substance, into like a vacuum sealed container at the triple point, what would it look like? You would see some gas space above the liquid, and you would see solid chunks in the liquid. So, I mean, it wouldn't look all that interesting, because what you would really be seeing is like a glass of ice water with head space, you know, like with air space, but sealed. Though actually, would it be, because you'd have particles escaping? I don't know. We'll have to see if we can find a video on it. But yeah, all three phases equal. Okay, so then you have critical point, and that's the junction of critical temp and critical pressure. Above critical temperature, the substance cannot exist as a liquid, no matter how hard you push on it, no matter how much pressure it's under. A phase diagram is going to show you the normal melting and boiling point. And to find that, what do you need to do? Well, you need to look at normal atmospheric pressure, and there it is. And then that gets you down to here. What you will notice on many of the phase diagrams is that the scales are not linear. Note that, you know, this is presumably 0. This is 1. This is 0.006. Huh? So to read these, what you have to do is divide spaces in half. So, you know, the first red mark that I made would be half of the distance between 0.0006 and 0.006 and 1. So 1 minus 0.006 divided by 2 tells you that this is, you know, I'm going to round the numbers here, it's approximately 0.5. Well, half the distance between those is going to be half the distance. So you're doing this sort of breaking it down into smaller chunks to read temperatures and pressures on this. That is important. Okay. This is just a little review about how special water is. And I've got my sexy water molecule up here. Water's only attracted to two things in the entire universe: itself and everything else. A young lady who drew that is now an art major at college and doing wonderfully for herself. But that was what came to her mind when she heard that. I love chemistry cartoons that people draw me. So, it's a bent molecule, and you know that, and that's because you have those unshared electron pairs on the oxygen, which pushes the hydrogen down. Now, here's what I think you know. We talked about it a little bit, but you may not remember it. Why does ice float? It's a good thing it does, or life as we know it on this planet wouldn't exist. Because the ice would sink to the bottom and then the whole thing would freeze. You wouldn't have liquid water underneath ice, and it would just freeze solid and stay that way. Who knows? Just wouldn't work out, is the assumption. Okay, as a liquid, the bond angle between the hydrogens is 104.9. When it freezes, Mickey's ears actually lay down, and that bond angle becomes 109. Which means that solid water is a little bit less dense. It takes up a little bit more space per unit volume. It's a little less dense than liquid water, which is why ice floats. Water, interestingly enough, is the only substance in the universe that we know of that does this. Most substances are more dense in their solid form than in their liquid form. Water's just an exception. And really, just stuff we already talked about. So it increases the bond angle, and it's got an unusually high molar heat of vaporization and heat of fusion. So makes it a great energy storage medium, makes it a great cooling medium. It can absorb a lot of energy from another substance before it will phase change on its own. So that is it. Here's what we're going to do. I'm going to give you a practice sheet for phase change stuff. I'll let you work on that, and I'll just post the key tomorrow. I'll give you points for having completed it all. Monday you will have a quiz. There will be some conceptual stuff like the homework, and there will be some using vapor pressure diagrams and using phase change diagram questions.